All right, guys, we have previously dwelled in the world of structured query language. We've lived our life imagining data as tables. And then we became exposed to JSON and XML. We realized that there are other ways to orient our objects in a hierarchical fashion. But we have not previously seen databases which are oriented to non-structured or semi-structured data. So enter the solution, which are NoSQL and one of its children within that hierarchy, MongoDB. So NoSQL just stands for not only SQL. So it can handle structured databases, but most of its types of categories are unstructured or semi-structured. It was developed to make a more scalable database, and it specifically tackles narrower business focuses. If SQL is like a file cabinet, NoSQL and MongoDB are more like a broom closet or a utility closet where you can throw literally anything you want in there. It's not as easy to find what you're looking for, but you can fit pretty much anything. You can put a whole lot of stuff in NoSQL and MongoDB. Data consistency is a little bit lacking, and you'll find that the fields are not going to be the same from one object to the next being stored in a NoSQL database. So let's take a look at the 4 types of NoSQL databases. So what we're primarily going to be looking at are document databases. MongoDB is one of those. Key value databases are a very simplified version. It's basically just one big dictionary, an entire database that is dictionary, and every entry, key value pair, is a part. I have never used a key value database in my work, but I'm sure there are people who do. Wide column stores. This is going to be, we've primarily worked with long form data. We're going to have a little bit of playing around with wide data when we get to time series. And then graph databases, talking about nodes and edges. In intelligence, we use a lot of nodes and edges. We have a content database that we use primarily based on this. It makes it very easy to track relationships between one sector and another sector. But for tonight, we're going to talk about MongoDB and document databases. So instead of tables being contained within the database, it uses JSON-like syntax. However, it is still written in C++, just like the underlying machinery of SQL is written. It is unstructured, and these tables aren't really going to be tables. They're going to be called collections. And every collection is like a broom closet. And inside of the broom closet, you can throw a bunch of different documents, be that a box of paper clips or a bunch of files or some chemicals to clean the floor with. And the documents don't have preset schemas. You can make up your schema on the fly and select new and different fields for every single different document that you have, but they can go in the same collection together. So how do you decide when you want to use SQL versus NoSQL or MongoDB? Well, I'll tell you this, if you want to use anything with XML, MongoDB is not going to help you. You're going to need to stick with structured query language. If you want data consistency or for somebody to be able to follow behind you and keep track of what you've done and make models, you probably want to stick with SQL and spend a little bit more time. If you are not super keen on documenting, but you just need to collect a bunch of stuff, MongoDB will take care of you. We have found ways to use SQL for free, but MongoDB was meant to be used for free from the beginning. Also, you can't join, no joins in MongoDB. You just make new collections and new documents based on existing documents. If you get down the road and you want to do Apache, Hadoop, you can't MapReduce with MongoDB. If this doesn't mean anything to you yet, just stay tuned. We'll get to PySpark a little bit down the road, and you'll see the glory that is MapReduce. So who does not currently have MongoDB installed?
I have no idea if I do or not.
Then you probably don't. So fortunately for you, I anticipated this, and our first activity round is going to be watching the video or following the prompts and getting MongoDB installed. So for folks at home, we're going to pause the recording to make sure everybody has MongoDB up and running on their OS.
All right, so for this part of the lesson, we're going to be using the MongoDB Students Notebook. So if you want to pull that up now. And so since we're kind of coming to the end of Mod 2 here, I wanted to bring things full circle and kind of revisit some data we looked at in our SQL study group, which is Pokemon. So for this, we're going to kind of create some of the same data structure we had in that SQL database, but in a MongoDB database instead. So to get started, you'll want to go to your terminal and just run MongoD, all one word. That will get the MongoDB server up and running and allow us to talk to it through Python. So I'll give everyone a second to run that command there. And just give me a thumbs up when you've ran that and didn't get an error message. Is that everyone? Beth, did you get it working?
No, I haven't gotten it working yet because I didn't realize PyMongo was a completely separate thing.
Yep.
So I'm working on that right now.
Okay. So yeah, for that, all you have to do is do pip install pymongo in the terminal, and that should work pretty quickly. But while you're getting that, we'll go ahead and just import our libraries here. We actually aren't going to use SQLite 3. I was going to kind of bring in that other Pokemon SQL database before, but we aren't actually going to use it. But we need pandas, we need requests, because we're going to talk to an API in this. And then we need JSON, and we need pymongo. So with those installed, we want to go ahead and create our Mongo client. We want to create our Pokemon database, and then create our Pokemon collection. And so we'll do all that here in this cell. You'll notice the address you pass into the Mongo client is just kind of the default one that the server runs at. It should say that in your terminal once you run the MongoD command in your terminal. All right, so now we're going to insert some data into the database. We're going to take the Pokemon Pikachu and we're going to add it, adding its name, its primary type, its secondary type, and its level. And this is kind of how you want to structure data that you're adding to the database. It's kind of just a dictionary with key value pairs. And then you can run the insert one command on your collection to insert the one entry. And we'll go ahead and do that here. Maybe in the bonus part, we'll have them evolve too. And then to kind of see what we have in our collection, we can use this command here. You use find on the collection. And if you pass in just an empty dictionary, it'll just grab everything in the collection. And then we can iterate through each of the entries in the collection and just print them out here. And I actually have two because I ran this before, but you all should just have one. And now we're going to look at inserting multiple entries at once. So here's the three starter Pokemon: Charmander, Bulbasaur, Squirtle, all their names, types, secondary types, and levels. And then we just want to create a list of all of them. And then we can use insert many instead of insert one and just pass in the list of all of their entries. And once we run that, we can also, again, check all the items in our collection. And you'll notice I added something here to the find. I added a dictionary with name set to 1. That tells it that I definitely want to return name. And then I have underscore ID set to 0, which means I don't want to get the ID back. Because if you go up here to the Pikachu example, you see that we got the ID back here, and it's just some random object ID. That's just included with every entry, but we don't really care about that. So setting that to 0 will just ignore it, basically. So when we run that, we just get the names of all the Pokemon in the database. So MongoDB, you can do queries on it too, kind of like SQL. You can do almost anything you can in SQL besides joins and related things. But so say we want to get all the Pokemon with a level less than 20. The way we do that is find again, and we again pass in, we just want the name and not the ID. And then in this first part, we pass in the level because we want to look at that. And then this $LT means less than, and we want the ones less than 20. So that's kind of the structure you have for queries. This link here will give you a list of all the others. You can do greater than or equal to, pretty much any other operator you could think of. So if we run that, we'll get the 3 Pokemon with levels less than 20. So now, especially in my case, because I have an extra one, we need to delete an entry. So with that, all you have to do is run the delete one command, and you can pass in, I could pass in anything here. Right now I'm just doing the name equal to Pikachu, but I could also do like the level, only remove Pokemon at a certain level, or I could use a query selector and select the Pokemon with a level less than something. So here I'll go ahead and delete Pikachu, and then I just print out how many items were deleted, because sometimes it'll be more than one. And then I can print all my entries. You'll see Pikachu's gone on your side, but I still have one left in mine. And now we can also delete many items, and we do that with delete many. We want to delete all the entries without a secondary type. And just in the way we created all the Pokemon, if they didn't have a secondary type, we just set it equal to none. So if we go back here and we delete all the ones where secondary type is equal to none and check the count, we should have deleted 3. And now we're left with the only Pokemon with a secondary type, Bulbasaur. And lastly, we just want to clear out the entire database because we're going to kind of rebuild it in a different way now. And you can do that with delete many and then pass in just an empty dictionary. So if we run that, it'll delete everything. And then just to check, we can run a find and nothing was returned. So everything was deleted. All right, so now we're going to kind of start collecting some data to put in the database. We're going to use an API called Poka API. It basically has all the information on anything Pokemon you could ever want to know. It has all the different Pokemon, all the stats about them, and even some stuff about the games. ETL stands for extract, transform, and load. That's kind of the process you go through when you build a database. You extract the data from some source, in this case an API. You transform it, get it into looking how you want it to, and then you load it into the database itself. So to connect to this API, we need to first get our base URL, which is this here. And we'll go to it here, the documentation, to see how we can get information on Pikachu. So I'm going to go to Pokemon and Pokemon down here. And let's see. So to make a request to get information about a specific Pokemon, it looks like I need to make a request to this URL endpoint here. So it needs to be /Pokemon and then / the Pokemon's name or ID. So if I go back here, I can make a URL for Pikachu and just append the /Pokemon /Pikachu. Then I make a request to that URL. I get the response back and get the JSON of it, and then I can check the keys. So from that, I can see all the different things that are listed here that I get back, abilities, forms, moves, height, weight, all stuff like that. And so now I'm interested in primary and secondary type. So for that, I actually need to go back to the documentation here. I can see there's types, and the type endpoint is just /types and then the type name or ID. So this example has ground with an ID of 5, and it tells me all sorts of different things. Let's see, I can see damage relations. So if you remember back to the SQL lab, we were concerned with what Pokemon had moves that were super effective against another type. So this here has a whole dictionary of types that it takes no damage from, that it deals double damage to, so on and so forth. So if we want to get the types that Pikachu is weak to, we can first get its primary type. So we do that by getting, getting the types of the Pokemon from this request up here. And then it's going to be the first type. And then from that, if we go back here, so we get a list of Pokemon types, and it should return us a URL that goes to the types endpoint. So all we do is grab that URL, and then Pikachu doesn't have a secondary type, so this is going to be none here, but this just checks if it does have a secondary type. Since it's a list, we just check if the length is less than 2, and it doesn't. But then if we run this, we can see it prints out the name, the type, the link to the electric type, and then this would be for the secondary type if it had one, but it doesn't. So now if we go to the electric type endpoint by creating this URL here and get the response and check the keys of the response, we can see all these items we get back. We can check the damage relations, and we'll do that now by checking the keys on that. And so we can see double damage from, double damage to, and in this case, we're concerned with double damage from because we want to see which types it's weak to. So if we check that here, we'll see we just got ground, and then we have the URL to the ground type. And the way to do this then in kind of a loop is shown here. For Pikachu, there's only one type, so we'll just get ground back. But if it was a different Pokemon with multiple types, you'd get kind of a list here. It basically checks the damage relations dictionary and then the double damage from, and it goes through each one in there and grabs the name of it and then adds it to the list. So with all that, here's the activity. You're going to kind of compile a Pokedex of the original 151 Pokemon and load it into a Mongo database. So to do that, you'll use this Poke API. It's a pretty easy one to use. You just have to kind of modify the URL endpoints to get the Pokemon, to get the types, and then the weaknesses. And this is the data you're going to compile. You want the name of the Pokemon, the height, the weight, primary type, secondary type, the weaknesses, and the moves. And then just a short note here for weaknesses. You want to look at both the primary type and the secondary type, but they could both be weak to the same thing. So you don't want to add that weakness twice. So you want to kind of check if you've already added something to your list of weaknesses to not add it a second time. And then just a hint, the first 151 Pokemon have IDs from 1 to 151. And if you remember, the endpoint for Pokemon info could be either the name or the ID. So you can imagine you could just have a loop here for numbers from 1 to 151 and plug that into the URL for each call to the API. So that's kind of the main activity. If you get through that quickly, there's a bonus here, digging into some more Mongo queries. I've linked some references and then put some questions here that are similar to the ones from the SQL lesson. What are the top 5 tallest Pokemon, so on. So you can kind of see how you would do those in Mongo versus SQL. And then just as you're doing this, you should probably think about the difference between the structure of this database versus the SQL one. So if we go back to the SQL schema of the Pokemon lesson, we can see we had weaknesses in a separate table. So to get the weaknesses of a certain Pokemon, you know, we'd have to do multiple joins and kind of go back and forth between the tables. But in this case, when you compile it in MongoDB, you'll just have a whole list of weaknesses for each Pokemon. So in that way, it's a lot better and easier for this situation than SQL. So with that being said, we'll go ahead and pause the recording.
Cool.
So let me go ahead and share my screen. All right. So here's the function I used to, I guess not function, more just a for loop that I used to get the information I needed. So you can see here, I started by just doing I in range of 1 to 152, so I can get all the 1 through 151 IDs for the original 151 Pokemon. From there, I set up the URL and then just format whatever ID number I'm on to the end here to get my URL formatted correctly. And then I just go ahead and get the JSON version of from the API call. We were having some debugging issues trying to figure out what was going wrong with mine initially, so I just threw in some print statements here to make sure I was getting the right information back. That's why you see these here. So from there, I do my initial dictionary structure that I'm going to actually insert into the Mongo database. Just do name, Pokemon JSON name, height, weight, moves. Primary type is just the types 0 type name, basically the same way Matt got the name out earlier in his stuff. And then also did, I liked Matt's kind of ternary style operation here to do none if this, else look at the second index inside the types array to get the type for secondary types. From there, basically you take this to get the type 1 URL. And then you just do obviously type 1 response. You go call that URL to get the API response. And then you start your weaknesses list here. So this is basically the same way that you get the damage relations double damage from that Matt did above. And then you check to see if there's a secondary type. I'm sure there's a more elegant way that you can incorporate doing like secondary, if Pokemon Dick secondary type is none, so that you don't have to do a double evaluation of this. This is how I decided to go about seeing it, because you don't want to call a second URL if there is not a secondary type. And then basically do the same things here. So what this is right here is this is taking this weaknesses list above and just concatenating the same thing for the type 2 response. So then from there, to dedupe the list, I initially did just weaknesses equals the set of weaknesses. But when we ran that, actually PyMongo couldn't encode class type of set into a MongoDB entry. So you had to turn it into a set and then turn it back into a list here. So that's just what I'm doing here. Then I'm appending that to the Pokemon dictionary here under weaknesses. And then obviously just inserting it in here. And then it'll do that for all 1 through 151 Pokemon. And then if you go up here and do this. So if I go now here, you can see here's all the Pokemon and their weaknesses, and you can even do, we wanted to see all the information to make sure it's all there. I'll delete that out. You can see. Oh, that's very, very large, but here's our moves list. If I had to go back and do it, I hadn't seen the moves before. This is obviously probably a lot of information. I would probably just go back and iterate through this moves array and do move name for all of them. Because it's taking up a huge amount of space here. As you can see, this is still all just the moves table. And you keep going, and you keep going, and you keep going. Wow, this can learn a lot of moves. But anyways, I think that basically verifies that it works. I'll go back and resort through all that. That's the first time I've seen the moves printed out. It's very large. Cool. That was my solution.
Nice. Good job with that. Yeah, the moves is actually a really big dictionary of like other sub-dictionaries if you get into the documentation. So ideally you would just grab like the name or something from it, or you could actually parse it out a lot of different ways. You get like the type of the move, the level it learns it at, things like that. But that at least shows you how like a MongoDB database can really contain a lot more information than a SQL one, because it can store like a nested dictionary like that. So yeah. All right.
If you want to pause recording, then we can take a quick poll on what our weekly challenge problem should be.